Hi everyone, thank you for joining us today for our presentation on offline robot programming with Octopuz. My name is Chris Height, and today I'll be giving you a brief introduction to offline robot programming as well as a look into the Octopuz software. First off, what actually is offline robot programming, or OLRP? It is the programming of industrial robots on a computer rather than on the teach pendant of the robot. Teach pendant programming is slow, frustrating, and forces you to take your robots out of commission in order to teach new programs. Taking this programming offline to a computer makes the process much faster, easier, and allows you to keep your robots working while creating new jobs for them. So how does Octopuz fit into all of this? We are a brand and application agnostic offline robot programming software, which means that any brand or model of robot doing any application can be programmed offline, all within our software. Octopuz eliminates robot downtime, it reduces programming time and complexity, and eliminates the need to own different OLRP softwares for different brands of robots. The most common robot application that we see the software being used for would be welding. However, we do see it very commonly used to also program plasma cutting and trimming, machining, milling, deburring, and other CAM operations, 3D printing, additive gluing and dispensing, as well as painting. Now let's take a look at the software and see how it works. Here we can see an ESAB XC1300 pre-engineered welding cell built up within the Octopuz software and ready to program. The part has also already been loaded. I'm going to hide my fences, and then let's zoom in to take a closer look at the part we'll be welding. We'll start by generating some welds on this feature right here. I'll select the two different faces that I'd like to weld together. Let's say this face and this face. And the software will automatically find the intersection between the two faces and generate the preview of the weld path that will be needed to accomplish this particular weld. We can make more precise adjustments to the location of the weld by applying offsets. As I add offsets to the beginning of the path, the end of the path, and the stick out of the tool, we can see that the preview of the path is being updated to reflect what our new path will look like. Once the path location is determined, we can go ahead and change the torch orientation throughout the path. I'm able to tilt towards either of the faces that I'd like to weld. I can adjust the flare in order to create a push or a pull on the weld that we're creating. And I can rotate the torch throughout the path about the wire axis. Next, I'll adjust the air moves leading into and out of the path. By default, they're coming directly down into the path and pulling directly up out of it. Let's say I want to make these much shorter. I'll scroll down to where it says leads and select this gear icon to view the more advanced options for the leads points. Here we can see the menu where we can make changes to everything about these points, such as their distance, the number of points, their direction, whatever it might be. I'll adjust the distance down for the first point from 200 millimeters to 50 millimeters. And I'll do the same for the last point as well. Now the preview shows the path with much shorter leads points on either side of the path. These are quite a few settings that I'm not going to want to make changes to every single time that I create a path, so what I can do is save a template of these settings to be used later on. For example, if I return back to the main path creation menu, when I'm creating a path in the future, I can select a template that I've saved out of this menu right here. I happen to have a template already saved in here for shorter leads, which use the same settings. In the future, when I'm creating welds, I can just simply select this template and it'll apply these settings for me automatically. Applying stitch or intermittent welding is done much the same way. I'll zoom in for a closer look. We'll click on this gear icon to see the more advanced stitch welding options. I'll start by turning the stitch welding on, and then all I need to do is specify the stitch length and the stitch spacing. Let's say, for example, we're doing 5mm stitches with an ISO spacing of 15mm. The software will calculate for us where the stitch welds are going. We do also support AWS spacing. And we also make use of even spacing, where we simply define the number of stitches that we'd like to see evenly spaced throughout the path, and the software will calculate the spacing for us. Just like with the leads motions, we can save a template of these options. I'll leave my stitch welding off for now. Multipass and multi-layering is done much the same way. We can go into the advanced menu, turn multipass or multi-layering on, choose the number of layers we'd like, the base thickness between each layer, and then we can see all the different layers that will be produced. We are able to change everything about each one of these individual passes as we could about a regular path, such as offsets or tilts or anything like that. Just like with the stitching and the leads motions, we can also save a template of these settings. I'll leave multipass off for now. The final step is to determine the behavior of the rotary axis throughout the entire path. I'm going to configure my rotary axis to cradle the weld bead in the 1F welding position the entire time to have the torch pointing downwards throughout the path. I can save a template of all of the parameters which I have set while creating this path to automatically apply them to future welds that I create. I'll call this my path template. And then I'll hit create. Here we can see the points of the path that we've created. Let's jog our robot to them. The path looks good. I'll go ahead and create another one. I'll use the exact same settings as was used with the My Path template and create another path here. There's my second path, and I'll right away create my third path. And now we've generated these 3 weld paths. Now if we want to create the same welds on the other side of the part, on the feature mirrored to the other side, we could create them one by one. As we've seen, it would be quite quick to do that. But if we wanted to be really efficient, we could select the 3 paths we've already created and simply mirror them to the other side. So that's exactly what I'll do. I'll select these 3 paths, I'll click on Transform up in the top ribbon, and I'll mirror the paths from this side of the part to this side of the part. Here we see a preview of the new paths that will be created. I'll click on Transform, and there are my new paths. Now I'll create a path along this weld right here. Again, I'll go into the Path Creation menu, select the 2 faces I'd like to weld together, and you'll notice that this torch preview is slightly different. A flare angle has already been applied to the beginning and the end of the weld. The Path Creation has done this automatically to ensure that the nozzle of the torch does not hit the part throughout this path. Now I'll select all the welds that I've created on this side of the part, and I'll mirror them again. This time mirroring them from this side of the part over to this side of the part. The previews seem to be correct, so I'll hit Transform. and there are my new paths. Next, we're going to want to run a check on the entire program that we've created up until this point to see if there are any kind of errors on the robot. I'll start by running the analyzer. The analyzer will go through our program and search to see if there are any collisions, joint limits, singularities, unreachable positions, or any multi-turn issues throughout the path. The report lets us know that we do have 2 points that are in singularity throughout the path. The point editor has also highlighted exactly which path and which points the issues are located in. I could resolve these manually, but I'm going to have the solver fix them for me automatically instead. I'll click on Solve, and I'll have it check my entire program. This has gone through, and it has fixed the singularity issues for us automatically. We can close this and watch our simulation. Once we're satisfied with the program that we've created, the final step is to produce the robot code in order to run this on a physical robot. To do that, I'll simply select the code option up here in the top ribbon. This will open up a file explorer to let me decide where I'd like to save the file and what I'd like to name it. I'll call this demo post. And you'll notice that it's already prompting me to write this out as a job file for a Motorman robot using a DX controller. This highlights that within Octopus, it doesn't matter what brand or what model of robot you're programming, the process for programming is all the exact same. It's only now that when we go to post the code out, the software will determine for us automatically which brand and model of robot and which robot controller is being used, and it'll call up the post processor needed for that specific robot. I'll hit save. And here we can see the code for the program that we just created in Octopus written out in the Motorman language. So as you can see, Octopus makes programming your robots very quick and easy. In under 15 minutes, we've programmed a new welding job on our robot, which includes 14 different welds and nearly 140 points. We've also verified that this job can be run on our robot without any collisions or other errors. And programming an operation like this on a teach pennant would have taken hours, even for the most skilled robot programmers. And so this represents quite significant time savings, not just for those of us who need to program our robots, but also for the robots themselves, as they can remain in production while these new programs are created. Let's quickly look at a few success stories of Octopus customers who've improved their businesses by using Octopus to program their robots. First is a yellow goods manufacturer, so they're producing agricultural, earth-moving, quarrying, and construction equipment. They have a large number of FANUC robots, about 30 of them at their facility, as well as a few ABB robots. All of them are welding. Before using Octopus, they were programming everything on the teach pennant, and their robot programmers were relatively inexperienced. Their programming time was dragging on for days, and their robots were being underutilized. But by switching to program with Octopus, they were able to bring programming time down to a maximum of just a few hours with no downtime on the robot. So the robots were able to be used more, and they were also able to program both brands of robots all within the same software. The second is a customer manufacturing plastic products. They currently have 5 FANUC robot cells. The programming time on the Teach pendant was so long that the robots were only running about 20% of the time. This caused a lot of frustration with management because, similar to our first example, they had purchased expensive hardware that wasn't being used very much. So by switching to Octopus for programming, they were able to keep all 5 robot cells running pretty much constantly because they could program them much faster and they could program them without taking the robots out of production. So these two examples show that the size of the organization doesn't really matter, and neither does the application that the robots are doing. Octopus is able to add value in all kinds of situations and businesses. Thank you all for taking the time to watch this presentation. We will now be taking questions.